Hi, everybody. I'm Ryan Grant. I'm from Queen's University in Canada. Now, you probably also know me. I used to be at the US DOE at Sandia National Labs for years as well before this. So, plenty of interest over time in workflows. And Ian Buckley, one of the other co-chairs for this breakout session, asked me to give a little bit of an update about some of the stuff that we're doing here at Caesar Lab at Queen's in the context of our current workflow update here in Canada. So Canada is looking at workflows. We already have quite a few elasticity requirements in our national supercomputing infrastructure that we serve through cloud computing. This is mostly through OpenStack and Mistral for developing these workflows. But there's interest in getting significantly more sophisticated with these things. Here at our local Queen's Supercomputing Center, we've been looking at quite a few different options for workloads with integrated molecular dynamics and flex models for crack and break simulation, as well as studying the flexibility materials. This relates really tightly with our materials folks and our medical school that are here that do quite a bit of this type of simulation and require much more complicated workflows than a standard Slurm type workflow would provide to you. So we're looking at much more sophisticated workflow models, things like covalent from agnostic, as well as a variety of different other options. We mostly have traditional workflows in terms of there's quantum interest that's happening here. And I know there's some in the States as well, but there's not really any production apps yet. So we're interested in how these things work together with workflows, but they're not the top thing that's on our mind right now. We're trying to solve our problems with workflows and reliability in particular. With our more complicated joined applications that we need to do at the same time. So sometimes we're doing both integrated molecular dynamics with other models built on top of them for things like that crack and break simulation, as well as visualization at the same time. So we have some interesting workflows on that side. And I was previously at the DOE and NSA, so I'm familiar with all the different workflow management that's going on there in terms of SAW at Sandia, Maestro over at Livermore, B at Lanel. We're taking a look at those items as well, because they fit well into our current needs for workflows with things like molecular dynamics, but they may not be generic enough all the time for some of our more national interest in terms of how to do workflows. So my work has mostly been concentrating on how to solve problems that we are finding through our workflows. And one of those big ones is reliability and elasticity. And so I'm working on the system software side and even some high-level architecture side to try to add in features that will enable our workflows to work better than they are today, especially around failures. So one of the elements that I've been working on, and I still collaborate with US National Labs on these, is one of them is called virtual memory access, remote virtual memory access. And this is basically a addition to RDMA or a replacement for remote direct memory access, the way that we move data efficiently around our system. But it provides the first opportunity that we have to actually try to recover RDMA buffers when things fail. So right now in the MPIs, the world that you're using right now, if things fail, those windows just become junk. You can't really do anything with them. You can't determine their state. And we basically have to fall back on checkpoint restore. And we don't want to have to do that. So RVMA provides an ability to actually do an RDMA type recovery because we've got buffers hidden behind the scenes. Like we have over here, we have actually multiple buffers in a queue. We can go back to the state of previous buffers from different communication rounds. We're hoping that this helps us avoid checkpoint restore in our workflows, and we can actually do some dynamic recovery while they're running that we wouldn't otherwise be able to do. And then the other thing that we care about quite a bit out of this is that the receiver controls resources and abstracts them somehow. So RVMA helps us abstract communication buffers, and this makes it a lot easier to support workflows in that receivers aren't necessarily tied to sending hardware in any way. So we can move communications, we can resize things and move processes around between systems without requiring changes on both the sender and the receiver side, because RDMA up to this point was entirely controlled on the sender side and knew low-level details about the receive side resources. And we're working with different hardware vendors on adopting some of these features as well, but these were key to us for both the reliability and increased elasticity by abstracting away some resources, but still getting very high performance with remote direct memory access. One of the other things that we're looking at is more sophisticated optimization and coordination within workflows. So we've been developing some new intelligent system software on SmartNICs or DPUs. These are basically network cards that have compute capability in them. Anything from, NVIDIA even has GPUs sitting on network cards, GPU cores up there for significant compute power. We're assuming that we can have a relatively lightweight SmartNIC in future generations of systems. And we want to use those to provide a non-interfering system software so that we can coordinate and optimize workflows dynamically as they run instead of just static allocations today. So these are understanding where and how we're using the resources within the allocated resources for that workflow, and how we could potentially use them better on a dynamic nature and react to changes in the workflow without necessarily the system itself understanding how the workflow is changing. Can dynamically adapt as sizes increase or decrease, or new elements are added to the workflow, or doing different types of computation or communication. And so we're really trying to make that elastic and adaptive as a whole. And the first part of the work that we've been doing on this area is really trying to make sure that we don't get in the way of the system. So the first thing that we've been doing is working on predicting application traffic and interspersing this coordination or optimization traffic into payloads where we have quiet network slots. And so far, we've been really good at this with relatively very small computation overhead. So you can see here on a molecular dynamics run, because we care about molecular dynamics, with something like LAMPS, the simulator, we can get down into very, very small normalized root mean squared errors in predicting when or when not we have quiet communication periods where we can send this type of traffic with these types of things. We can get down to errors that essentially mean that we're 100% of the time, 99.999% of the time, we can send at the right period during these applications. Now, the next thing that we'd like to look at, because we've only been looking at relatively simple workloads here, is also combining together workloads as they change dynamically over time. That's going to be a more challenging problem to be able to fit our traffic in between, but we're building there in that area, and we're trying to come up with new methods of optimization and coordination here as well. So hopefully we'll have a good high performance modern system software stack in a place that you never had system software before, that doesn't get in the way of computation, but provides optimization and better coordination opportunities for your workflows in the future. And with that, Rosa, I think I'm with my 5 minutes. So